Lesson 3.2 had us working with systems of equations. So chapter 3 starts into systems of equations. So again, that means that you have more than one equation and that you're trying to either find the solution for, or you're trying to see if those two equations share any solutions. So that's what it means to have a system of equations. It's two or more equations. Right now, we're just working with two. In 3.1, they gave us the first way to do that, the first method, which is graphing. You can graph the two equations and see either where they connect or possibly if they don't connect at all. If they're parallel, they will never cross, which would mean they don't have any solutions. So for the graphing aspect, we were actually able to see it visually, see where they either cross once to give a solution. They are graphed on top of each other, which means they have an infinite number of solutions that satisfy both of them, or they never cross at all, which means they're parallel and they don't share any solutions. Okay, so in 3.1, we were actually able to see it through the graphing method. In 3.2, they're going to review the other two methods, which are substitution and elimination. And these do the exact same thing. It's just that you can't visually see it on a graph. Okay, they're a little bit quicker as well. And in number one, they're going to start with substitution. So when we're substituting, we're going to take one of those two equations and we're going to solve for one of the variables. It doesn't actually matter which equation we choose. It doesn't even matter which variable we choose. So your work may look different than other people's work, or even the way I do it at times. But in the end, we should end up with, no matter how we do it, we should end up with the same answer. So for number one, I'm going to start with that top equation and I'm going to isolate x. Right, and when I do that, I get this. Okay, you could have isolated for y. It required less work for me to isolate x, so that's why I picked that. All I had to do was subtract that 2y. So now I'm going to go to the second equation. So this was the first equation. Let me write that above. Okay, so that was that first equation in number one. The second equation looks like this. And so now what I'm going to do is I'm going to take what I just solved for in the first equation and I'm going to substitute it in for x over here. So I've got this x equals 6 minus 2y. I'm going to take and drop that in over here for x. So what this does is now it takes where I had two variables. Now it puts everything in terms of y, and I'm able to solve for y and actually get a value. You can't do that. You can't solve for an actual value when you've got two variables in the equation. So that's why we have to do this. All right, so we get a y of 2. All right, so now we have our y. We need to get our x as well, though, so because we want the actual solution. When they say solve the system, they mean where, if these two equations are crossing, when you graph them, where are they crossing? We can't just give a y coordinate. We need to also give an x. So I'm going to take that y of 2. I'm going to pick one of the original equations, and I'm going to plug that y back in. I'm actually going to do it up here, where I already solved for x, and just plug it in right there. And then I see that I get an x of 2 as well. So the answer to this then is 2, 2, which means if we were to use the first method that we learned in 3.1, the graphing method, these two lines would cross at 2, 2. Let's move down to elimination. So this is the third way of solving a system of equations. They ask you to solve the system, meaning find where they cross if they do, and you're going to do that using the elimination method. So for eliminating, eliminating's great when you already have um, two coefficients that are the same value but opposite signs. So in number 7, we've got this negative 3x and this positive 3x. And that makes it very easy to say, let's just add these together. Okay, we're going to combine the two equations. If I add a negative 3x and a positive 3x, those are going to cancel out. I'm going to end up with 0x. So those x terms go away. 3y plus 1y will give me the 4y, and then 3 plus 9 gives me 12. And if I solve all the way down, I get a y of 3. So that, again, is part of my answer, but I've got to back up, plug that 3 back up into one of these equations. Okay, so I'm going to evaluate one of them at 3. I'll pick that second equation. And I'll get an x of 2 this time. So my answer for this equation, or the system of equations, would be if we were to graph them, we'd be able to visually see that they cross at 2, 3. So this is the solution to these two equations, this system of equations. On number 9, they want us to use elimination. So in order to do that on this system of equations, we actually have to change one of them because we don't have any variables, any coefficients that just match automatically. Like we did over here. We had that negative 3 and this positive 3. We don't have anything like that over here. So we're going to need to multiply one of these equations through in order to make the coefficients match. You could multiply through by 5 on this bottom because that would give you a negative 5x on the top and a positive 5x on the bottom. Or you can multiply through by 6. All right, if I do that, then I end up with 6x and negative 12y, and that equals that negative 36. You remember to multiply the constant by the 6 as well. Okay, there you're multiplying the entire, both sides of the equation need to be multiplied by the 6. Now, this equation is kind of obsolete at this point, and I'm going to combine the top one and this newly written one, this one that I renamed. All right, when I do that, the 12y and the negative 12y cancel out, and I end up with x of negative 16. Again, then I'm going to take that negative 16, I'm going to put it back into one of the equations. I'm going to use that bottom one even though it's hard to see now. All right. And when I do all the work there, all the algebra, I end up with a negative 5. So these two are going to cross. If we were to graph them, they'll cross right here at this point. Now on this bottom set of problems, they tell you that you can use any algebraic method to solve this system. You have 3 at your disposal. You've got graphing, which probably wouldn't be your first choice, the substitution or the elimination. And so if we go back and look at our different options here then, we're going to pick between substitution and elimination. If we substitute, we can do that, but we've got to do a lot of work to isolate for one of those variables in order to substitute because they both have coefficients. All the x and y terms have coefficients, so we'd have to do a considerable amount of work. We don't have to do that because elimination allows us to cancel these two 7s if we combine through addition. So we're going to do it that way just because it's a little bit less work. So I'm going to add. I don't even have to do any multiplying like we did in number 9 because we've already got coefficients that when we combine them, when we add them, we're going to get 0. All right, so we end up with an x of 1. When I take that and I evaluate 1 back in for one of these equations, just pick one of them, I will get a y of negative 1. So my solution for this system is 1, negative 1, and we used elimination to do it. All right, in problem 23, we have a description of a hair salon that receives a shipment of hair conditioner that they're going to sell to their customers. They received 84 bottles total. There are 2 different types of conditioners. There's a type A and there's a type B, and each of those has a different cost. So type A has that, it costs $6.50 per bottle. Type B, $8.25. The hair salon's invoice for the conditioner, meaning how much they had to pay to receive the shipment, is $588. So we're not talking about they've sold anything yet. We're just talking about how much they paid to actually receive the shipment to their store. They want you to tell them how many of each type of conditioner are in the shipment. So we're going to write out what we know first. That's always the best place to start, just so we can be free to not look at the words in the problem over and over again. We are going to sell 84 bottles total. Type A costs $6.50 per bottle. I'm going to take out the $sign and the zero, okay, so that we can not have extra stuff around. Type B is $8.25, so $8.25. The shipment costs $588 total. And they want to know how many of each type did they buy. So we're dealing in systems of equations here. This is how we're going to use it for a word problem. You're going to need to come up with two equations. All right, so equation 1 and equation 2. Equation 1 in this case is going to deal with the actual number of bottles. If you look up at the information we have, we've got number of bottles and we have money. So we're going to make one equation that relates the total number of bottles, and then we're going to make another equation that has to do with the money. For type A, we need to assign some variables. So type A, I'm just going to call A, and type B, I'm going to call B. All right, and that'll be the number of bottles that we sold there. Okay, so A represents the number of bottles of type A we sold, B, the number of type B we sold. So if you write down A plus B equals 84, that represents the number of bottles. Then we've got the cost to think about. Every time you sell a bottle of type A, you make every time you buy a bottle of type A, I think I keep saying sold. We're talking about them buying the shipment in from the distributor. So every time they bought a bottle of A, they had to pay $6.50 for it. Every time they bought a bottle of B, they had to pay $8.25. And then when all that was totaled together, they owed $588. So one of the equations is going to do with the physical number of whatever the items are we're talking about, and the other one is going to usually deal with money. So then we're going to use these two in order to solve the rest of the problem. Probably, so we could graph, again, probably not your first choice. We could substitute, which might be a really good option because you've got A plus B equals 84. A and B would be really easy to solve for. And you could also eliminate if you wanted to bother going through and actually calculating, actually multiplying something through. I think we should pick substitution here for this one. And so I'm going to take my A plus B, that top equation, and I'm going to solve for B. And then I'm going to take that and I'm going to drop it in for B in my second equation. Right, when you do your calculations, you should get this. All right, I'm just distributing at 8.25. All right, then when I'm going to combine like terms and do that subtraction. So I get negative 1.75a. I'm going to subtract the 693 from both sides. That'll give me a negative 105 over here. And then when I go through and do the division, I'll get an A of 60. So what that means then is that we have 60 bottles of type A. So 60 of type A. And if we have 60 of type A, we can go back up. We know up here in this equation, this first one, that if we have 60 of A, we're just going to subtract that from 84. Actually, we can look right here too. 84 minus that 60 lets us know that we have 24 of type B.